What is a polymer? The International Union of Pure and Applied Chemistry, IUPAC, defines a polymer as a substance composed of macromolecules. So this is a great definition if you know what a macromolecule is. And fortunately, IUPAC have also defined this for us. A macromolecule, they say, is a molecule of high relative molecular mass, the structure of which essentially comprises the repetition of multiple units derived either actually or conceptually from molecules of low relative molecular mass. Right. So, what does this actually mean? It means we've got a big molecule, relatively, and not just any big molecule, not a random big molecule, but a big molecule that we can divide up conceptually into small repetitive pieces with the same or a very similar structure. Whether or not this molecule is actually generated by putting those little molecules together, we can conceptually break it up in that way. So a very common analogy is to think of a linear polymer, linear macromolecule as like beads on a string, though of course there actually is no string. So our little green circles here correspond to our monomers from the Greek word for one, and all of our circles put together is our polymer from the Greek word for many. Let's make this a little bit bigger to demonstrate that there is no string. What's holding them together is the overlap between the electron density of those monomer molecules, rearranged to form this one big polymer molecule. And whatever reaction is generating this big long linear molecule usually has no particular reason to stop at any particular length. So a polymer can be of any arbitrary length depending on how it's generated, and you will get a broad spectrum of molar masses in any sample of a polymer. So there's that pseudo-Neo-Greek word there, monomerous, consisting of one part. These are what you would get if you got terephthalic acid and ethylene glycol and terephthalic acid and ethylene glycol and one more terephthalic acid in this picture and combine them together. This is a very short oligomer of polyethylene terephthalate, so common plastic used in making soft drink bottles. And you'd want to make that many screens wide to be effective for keeping your soft drink in the bottle. Or you could take ethene plus ethene plus ethene plus ethene, and I think I have about 7 of them there. That'll give you polyethene, and you can take a whole bunch of different amino acids, put them together, and that will give you a polypeptide. The word protein, I guess, is an older word than polypeptide, which doesn't reflect its polymeric nature. And this illustrates one of the actually or conceptually built up of smaller molecules things, in that here the repetitive bit is the structure along the backbone. There are different things dangling off the end, but the repetition in that molecule, the order, comes from the fact that the essential functionality along the backbone is the same in each case. So we're actually or conceptually splitting up these big molecules in each case into these little things. Now, why are macromolecules a valid field of study in themselves? What differentiates macromolecules from common or garden little molecules? Well, they're big, and in a way, that's all there is to it. What this means is that their size dominates their properties rather than their chemistry does. So the physical properties that arise from the large size of these molecules will dominate how they will behave in solution, how they'll behave in vivo, etc. So this size means that they're relatively inert. So a couple of examples, just to think about how readily soluble glucose is, and then think about how insoluble cellulose is. And cellulose is just a whole bunch of glucose molecules stuck together in a long chain. Similarly, chloroethane, you don't want to breathe it, you don't want to get it on your skin, it's not really very good for you at all. But when you get thousands and thousands of chloroethane molecules knitted together, you get polyvinyl chloride, which is perfectly inert, and you could happily sit there and chew away on chunks of polyvinyl chloride. Actually, no, you probably shouldn't do that. But it's pretty harmless stuff, and we pump water through it all the time in our buildings. It's innocuous material. as well as conferring inertness on these molecules, their large size confers certain physical properties. So they're solids, but they don't behave in the unresponsive, boring way that crystalline solids do. They tend to be elastic. They tend to have resilience. And this is why they've been the main structural materials for plants and animals for billions of years. And in human civilization, they've also been the main structural materials. So once upon a time, our civilization was based on leather and wood and bone, all polymeric materials, and we dallied with metals and stuff for a little while. And now we're getting back to polymers again in a big way as the main structural materials for our civilization. We can conceptually divide polymers in several separate ways. Probably the first big way is in between synthetic and natural polymers. So natural polymers, all those things like leather and wood that nature kindly makes for us. Synthetic polymers are things we have to make ourselves. And within synthetic polymers, the main division is in terms of the mechanism by which we generate these macromolecules. We can split them up into step growth polymers and chain growth polymers. And I'll explain what these mechanisms mean momentarily. You can get a first little feel for it by looking at this picture and seeing that in the step growth polymer picture, there are all sorts of, well, basically one repeating functional group again and again along the chain. There's an ester group in the polyethylene terephthalate. Whereas with our chain growth polymer here, our polyethene, aka polyethylene, we do not have all those fancy functional groups in the chain. It's just one big, long carbon backbone. And this arises from the different mechanisms that create these two things. Here are some natural polymers. Mechanistically, most of them are created by a mechanism that's sort of in between step growth and chain growth, and I'll tell you a little bit about how they're constructed as we go along as well. So you're all familiar with nucleic acids, which we use not so much for their structural capacity, but for their information storage capacity. Proteins that do everything, in animals particularly. Polysaccharides, structural materials for plants. Energy storage materials for animals and plants. Lignin, this is another structural material for plants, and I'll show you some ugly pictures of lignin as we go along. Polyhydroxyalkanoates, a carbon storage material made by bacteria, and polyisoprenoids, things made by plants for various reasons. Bacteria and plants are much more clever chemically than we animals are. We have these opposable thumbs and we can go around and chop them down, and we think we're so great. But really, chemically, plants are much more innovative than we are. So what is this thing called step growth polymerization? Let us consider, first of all, this compound here, omega hydroxycaproic acid. So we've got a 7 carbons and a hydroxy group at one end, or carboxylic acid at the other. And obviously those two functional groups can react with each other if we have multiple molecules like this sitting around. So we get an ester like this. And this ester, you can see, still has a hydroxy group on one end and a carboxylic acid group at the other end, so it can react with more molecules of the same kind. And so we have this quite trivial esterification reaction that under certain conditions can just keep going to give us a great big long molecule. So these sort of reactions are also called condensation polymerization. That's because we're producing at each step a small molecule as well as our larger molecule. And if we were doing this by heating our omega hydroxycaproic acid in a vessel that was closed, actually, we wouldn't want to do that in a closed vessel, but in a situation where it was under reflux, we would have this water that was also being generated by this reaction condensing as the vapor phase of this reaction cooled down. And it's not always water. It could be hydrochloric acid, for example, if we're using a different substrate. So this term here is also applied to step growth polymerization. But not all step growth polymerizations are condensation polymerizations. You can imagine these cases where you have these functional groups being generated like so, in a reaction that doesn't also generate a small molecule. So step growth is the more general and preferred term rather than condensation polymerization. And we characterize different forms of step growth polymer by what this functional group in the backbone is. So if it's an amide, we call it a polyamide. So the nylon 6,6 here and nylon 6 are two common polyamides. This one has two sixes because it's made out of two monomer molecules, each of which has 6 carbons in. So this is our diaminohexane, and this is our sebacoyl chloride. Both have a 6 carbons in the backbone, and they give us this amide group. Nylon 6, we see we've ended up with a very similar sort of compound, and that is from the ring opening of these lactams here. So I kick that off by putting some water in, and under the appropriate conditions, we can, instead of having a whole bunch of little molecules that are cyclic, we can have one big linear molecule. This same two ways of getting to very much the same molecule are illustrated here for polysiloxanes. Here are the functional group that's repeated in the backbone is this silicon oxygen silicon moiety, and you can make little crummy polysiloxanes by using this halogen containing silicon compounds like this one and water. So you get a copolymerization between this thing here and water, a condensation that's generating hydrochloric acid as the small molecule. But to generate the large polysiloxanes that we're familiar with in our silly putty-like products and lots of other more important industrial applications of the same stuff, these polysiloxanes, we take these little linear polysiloxanes, make them into cyclic structures, and then ring open those to give us our nice large polysiloxanes. So we've had polyesters, we've had polyamides. Another class of step growth polymer that you're probably familiar with are polyurethanes. This entity here is the urethane functional group. You see it's basically like an amide and an ester put together, where the carboxyl group is shared between them. And we make this by a reaction between an isocyanate and an alcohol. So these are quite classical ingredients for making a polyurethane, to make the sort of foams that we're familiar with. We have a nice rigid aromatic structure for our isocyanate, or diisocyanate, which we need for the chain extension. And for our diol, we have a polymeric structure. It is very common to have a long, either elastic or rigid pre-polymer with our hydroxy groups at the end, and then the hydroxy groups react with the isocyanate functionality to knit those pre-polymers together into a big molecule. Now, in this illustration, you'll see that we started off with 4 reactive groups, and 2 of them have reacted, and we can define a term called extent of reaction, which in this case is trivially 0.5. So our reactive functional groups at the end divided by our reactive functional groups at the beginning is 0.5, and for obscure reasons we give that the symbol P. Now, since the properties of a polymer are overwhelmingly dependent on how big that polymer is, a very important thing for characterizing any polymer, or the most important thing, is the degree of polymerization. So this is sometimes given the symbol N, sometimes X, sometimes we're more explicit and call it dP, and it's just the average number of monomer units that you have in a chain. And this simple equation here is the Carruthers equation, named after Wallace Carruthers, who's pictured on the right there, who was a very significant figure in the development of both step growth and chain growth polymerization. And like many people involved in the development of polymer chemistry, polymer science, he worked in industry, not in academia. So this is a field where university researchers really sort of struggled to keep up with and understand the things that were being done in industry. And I could go off on a tangent and tell you lots of stories about Wallace-Carruthers, but there are probably plenty of other videos out there telling the Wallace-Carruthers story, so I'll let you find those yourself. So for our polyurethane here, our extent of reaction was 0.5, so if we plug 0.5 into that expression there, we get 1 over 1 minus 0.5, or 2 for our degree of polymerization, which is an absolutely trivial result that we could have gotten by looking at that picture, yet it is correct, and it will be correct for whatever extent of polymerization we put in, extent of reaction we put into that expression. So say we had a much more complicated system, and we were looking at the infrared signal arising from that isocyanate group and monitoring that as we went along doing our reaction, taking little samples out, and we confirmed that 98.4% of our diisocyanate had reacted. Then we could put that 1 minus 0.984 into our expression here to find that in that case we would have a average degree of polymerization of 62.5. The Carruthers equation, as I've given it to you here, sort of relies on the fact that our reactive groups are being consumed equally. But we can have situations where we have different quantities of our two reactive groups, like so. And here we have to go to a slightly more complicated equation where we introduce another term R, where R is the ratio of the amounts of our two functional groups that are going to react to form that new functionality in the backbone, with the ratio of the smaller amount to the bigger amount. So like in this possible nylon 6,6 recipe where we have 70% of our acyl chloride and 30% of our amine, we use this form of the Carruthers equation, and so R is 3 on 7, blah, 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 and substituting it in, we find that at an extent of reaction of 0.5, where we would expect to see an average degree of polymerization of 2, in that a case where we had equal numbers of our functional groups, if we have this distribution of our two functional groups, our degree of polymerization goes down to 1.43. So any deviation from that perfect balance between those amounts of the functional groups will give us a reduction in our degree of polymerization. And it's pretty easy to see why that would happen, because you're going to end up with molecules here that are of two acyl chloride functionalities at the end. So basically this imbalance in the functionalities will limit the possibility for chain extension for molecules, because if you end up with more of these acyl chloride in groups than of these amine in groups, there are going to be some acyl chloride in groups that miss out. And you can verify for yourself that if you put R equals 1 there, that equation will simplify back to our initial form of the Carruthers equation. So here are a few questions for you to think about. We've just presented this Carruthers equation as a sort of fait accompli, but it relies on certain assumptions. So you should have a think about what those assumptions are. You should also think about what's going to happen with step growth polymerization if we try to make very large polymers. So if we want a polymer that has 1,000 monomer units in its backbone, what difficulties are we going to run into trying to do that? Why might we do things by these ring opening methods? What's the point of going to the ring opening methods rather than our simpler methods apparently simpler methods where we just generate a small molecule as well? So have a think about those things, and I'll return to you soon.